Hi, my name is Vera Mays. I'm with the TSC Learning Commons, and I'm one of the math specialists here. Our job today is going to be covering the second part of the MAC 1105, 1105C final exam review. We are going to start, let me get down. With solving equations. The first other things that you saw fly by are in part one. So join us for that if you need to look at those topics. All right, so the first problem under solving equations is a quadratic, and I know that because it's to the second power. And so we have several strategies to solve quadratics. Most of them involve getting it equal to zero. Unfortunately, this one is already equal to zero. And so one of our things we can do, we can try to factor it. We can use the quadratic formula. We could use completing the square. And a couple other methods like graphing and stuff. So, but this one I'm looking at to see if I can undo the foiling process. So I look at the factors of 6. So I've got 1 and 6 and 2 and 3. Because it's a positive, I know I'm going to be adding these together. So 1 and 6 won't give me the 5, but the 2 and the 3 will. So this one factors fairly nicely. So I'm going to put an x and an x for the x squared. I'm going to use the 2 and the 3. Now, because this is a positive 6, either you're both positive or they're both negative. The middle term tells us that they both have to be negative. Now, I'm going to use the zero property rule that if I multiply two things together to get 0, one of them at least has to be equal to 0. And we don't know which one. So we just assume it could have been either one of them. And we set both of them equal to 0 and then solve and get that x by itself. And so here's our two values of x that would be solutions that if I were to plug them in for the x's on the left side, they would go to 0, which means we would have 0 equals 0. The second one that we have does not have a first coefficient of 1. So it's not going to factor necessarily as cleanly. So we have some options. Like I said, we could use the quadratic formula. We could use completing the square. We could try to factor it using the AC method. So you have choices. I'm going to go ahead and do quadratic formula. So we know that our x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now this only works if it's to the second power, and that's what we've been focusing on in this class. So here's my a, here's my b, here's my c, because remember every quadratic is of the form ax squared plus bx plus c. So I'm just going to plug them all in here. Kind of doing it in a generic form so we can see where everything goes. Okay. And then let's do 3. So this is B. B was 3. That goes into both of these positions. A was 2. C was a negative 2. And then the 2 also goes down here. So you can see where I've done my substitutions. Now let's just go ahead and simplify. A negative times a positive is a negative, plus or minus. Let's see, 3 squared is 9. Negative 4 times 2 is negative 8 times a negative 2 makes it a positive 16. And then 2 times 2 is 4 on the bottom. So if I clean this up one more time inside that radical, I get a 25. Well, most of us have learned that the square root of 25 is 5, or you can put this in your calculator. It comes out nice and pretty. So this one would have factored because it doesn't have this radical here, but I just didn't see it right away. So I know that I have other tools. So now if I look at this, I need to break it apart to give me my two answers, -3 plus 5 over 4, -3 minus 5 over 4. So this gives me a -2 over 4, which if you put it in your calculator or you reduce the top and bottom by 2, you get this. This gives me a -8 over 4. Negative divided by positive is -8 divided by 4 is 2. So here are my two solutions for this quadratic. I could have tried factoring. I could have done the AC method. So I have options. Okay. Another use of quadratics is explaining what happens around us in the real world. So we've all thrown a ball up in the air. We know if it goes up, it eventually comes down, right? We know that this is the shape of a quadratic. They gave us the function using the gravity numbers. Whoops, not a cube. Okay. And this is describing how fast it's going, how high it is when it starts off the ground. But because we know it's a quadratic, it's going to go up and then it's going to come back down. At this point is going to be the maximum that it gets. This question is saying find the time to reach the maximum. If we look at the function, we can see that time is the independent variable. So for us, we're thinking that's normally what's in the x position, and then the h of t is what we normally think of in the y position. So if we're just wanting to find out this top part, we have the first part of the quadratic formula. And we're going to not use the part with the plus and minus, but then we're just going to use a negative b over 2a. That gives us the vertex, which is either the max or the min. And so in this case, here's our a and here's our b. So -96 over 2 times a -32. -96 over -64. And if I put that into my calculator, you can using whatever your teacher allows you to use. I love Desmos myself, but let's see, -64. I get a 1.5. Depending upon how they say they want the answer, because we know that some programs are more specific, you could ask your calculator to give you this as a fraction. In this case, because it's a real world example, typically the decimal's fine. Now I do want to put some units on it. This is time. Time in this case is in seconds. Okay, now to find the maximum height, we're looking at this formula that we were given, but we want to put the height at 1.5 seconds. We want to know how high did it go up before it decided to start turning around and heading back to the Earth. So every t becomes this 1.5. And then I'm just going to put this in my calculator with parentheses. I like the parentheses. It helps me keep organized. Let's see. So plus 96 times 1.5 plus 5. So this went up 77. And from the original numbers, we could see that this was feet. Right. Here's one that's not a quadratic. It's linear. And so some of the things we know about linear, it has a basic equation of y equals mx plus b, where the m is the slope part. That's the part that's changing. And a lot of times that's associated with the word per when we're doing real world examples. The b is in math, it's our y-intercept. But in this case, it's the base. It's your starting point, the part that's not going to change. This one is the part that's changing. This is the part that's not changing. All right, so I look back, want to kind of set it up. It's a cost function. So a lot of times they'll go ahead and label it with a C, and we'll need a slope and we need the base. This is a taxi. So taxis usually start out as a flat fee plus they charge more per mile. So this one has a $4 flat fee, and this one is saying $2 per. Remember, I said look for this word, $2 per mile. So there's my linear cost function. They gave me everything I needed. I had to know the basic setup. Now, a lot of times these are two-parters. So what they're going to do now that you have come up with a function, they're going to ask you to calculate the cost for a certain amount. So this is 8 miles. We just put it in everywhere we see an x, not changing the slope and not changing our base. So this ride of 8 miles would cost us $20. All right. We have a lot of business majors that take this class. So we have thrown in a few business type functions. Every business likes revenue. This is the money you bring in to pay all the bills. So they gave us the function, and I see that the highest power is not listed first. So I'm going to just go ahead and rearrange this, not changing any positive or negative, just like puzzle pieces, shifting them around a little bit. Okay, so here is the function. It's a quadratic again. It's got a negative, so we know it's kind of like a frown. And we want to find, the point at the top, right? The maximum right up here. So we know that this is an x and an r of x. So they could ask you how many you need to sell, or they could ask you how much revenue you bring in. So let's read what they're asking. Find the quantity that maximizes revenue. So they're wanting the quantity of things sold. That's our x value. So we know if we're looking just this top point, that's also our vertex. So again, we can use that negative b over 2a. That's what I'm trying to show you as I do these examples, is that this comes in handy a lot of different ways. We used it to calculate the height of a ball being thrown up in the air. Now we're using it in a business connotation. So let's go ahead and find our A's and our B's. So here's our A, here's our B. Let's plug them in. That gives us negative 50 over 2 times 0.5. This is a negative 1. And so negative divided by negative is a positive. So we need to find 50, and we don't know what we're selling. So we're just selling 50 items. We don't know what they are. They could be computers, they could be shoes, they could be pencils, who knows? But because it's a quadratic, we can use this vertex formula again to find the highest or the lowest point. All right. Solving equations. Not all equations are either quadratic or linear to start. Some of them are rational, which means they're in fraction form. And we learned a couple ways to deal with fractions. We could multiply both sides by the common denominator, or we could use the simplified method of using the cross multiply method. I'm going to turn this into a fraction. So we have 2 layers and 2 layers. Now, if you did it this way, you had one crossbar equal to the second crossbar. So the green one gave us 1 times x plus 2 equals, and then that red one gave us 4 times x minus 3. So you're just multiplying this bar and setting it equal to this bar. And now we're going to simplify, so we can go ahead and distribute, but we know that 1 times something doesn't change it. So I can just bring this down. However, this one I need to distribute the 4. All right. Nice linear equation, no squares, no cubes, nothing. But it means I need to be solving for x. That's what they told me. And I need to get the x's all on one side. Now, with linear equations like this, we learned it doesn't matter what side they go to. Some people always do the left. Some people do it where the x's are not going to be negative. Your choice. I see that there's a larger x over here, so I'm going to bring this guy over to join his buddy. This one does not have an x, so I'm going to take him to the other side. That leaves me with 14 equals 3x. Divide both sides by 3. So before I circle this and say this is my final answer, I need to look back at the original fraction. We know that we are not allowed to divide by 0. So we do have to take whatever is on bottom and set it equal to 0 to see what restrictions we have on this original function. So we find out that x cannot be 3, so that when we get over here, we see that this is not a 3. So I can circle it and say, this is my final answer. If this had worked out to give me a 3, I would have had to say there were no solutions for this equation. All right. This is a very specific method that I mentioned when I first said we were going to do in solving problems, completing the square. We are trying to get it to where the two factors are equal to some number. Then we can use our square root property and get to the x value very quickly. So completing the square. Now, some teachers do this. There's like 2 or 3 methods to set this up. What I had learned was to take this number that's with it, because the factors of 5 times 1, well, they would factor, but that's why I'm going to make our answer come out pretty. But assume this number is not the right number. Bring it to the other side. Now, to get it to this form where I have a binomial squared, I need to add something here. And if I do it to one side, I need to do it to the other. So this process says take 1/2 of the middle term and then square it. This is the number that I need to add to both sides. So now when I look at this part of the equation, I see that I can factor it. X and x will give me the x squared. Everybody's positive in this case. This number is always what goes into the factors. This one after you took the 1/2. Let's simplify this side. Looks like we get a 4. You can see that this is the exact same factor. So to condense this, we can do this and put it to the second power. So this is usually part A. When they ask you to do it by completing the square, they're going to set it up even and have you just fill in this part and this part. Now to actually solve it, I'm going to use that square root property. And whoops, I'm going to go to a different color. Go take square root of both sides. And when I do that, I have to add my own plus and minus. The square root of something squared, those are inverses of each other. So they cancel out and you get just what's on the inside. All right, we can simplify this. You could either use a factor tree, or this is one that we usually recognize. Square root of 4 is a 2. So now I'm going to go ahead and bring that 3 over. Put it in front of the plus or minus to keep everything kind of organized. So here's my 2 solutions. X is -3 plus 2. X is -3 minus 2. So this gives me a -1 for one of my solutions. This one, negative and negative, x equals -5. There's my 2 solutions using the completing the square method. Because there's no radicals here, that means that this would have factored nicely also. But it make the numbers nice to be able to follow the process. All right, another quadratic to solve. Again, we could use completing the square. Let's do that because it's a method that most of us don't see very often. So remember, we set it up, move that 13 to the other side. And the reason I say that completing the square would be nice is because that first coefficient is a 1, and this is an even number. Because remember, we're going to take half of the middle term. We really don't want to do that if it creates a fraction for us. So we're going to take half of the 4. We get 2. 2 squared is 4. So I'm adding 4 to both sides. Means this part now will factor beautifully. an x, and an x to give us the x squared to give us the 4. Remember, it's always this number. Everybody's positive again. If that middle term would have been negative, these guys would have both been negative. Negative 13 plus 4 gives me a negative 9. So x plus 2 squared equals negative 9. And then I'm going to take the square root of both sides, adding in the plus and minus. So this one, square root drops the square. Now remember, square root of a negative 9, that's square root of negative 1 times the square root of 9. We learned that we can represent the square root of negative 1 with an I. Square root of 9 we've learned is 3. We usually rewrite this as the number first and then that letter. So let's put that into play. Now we're going to bring that negative 2 over. So we've got x equals negative 2 plus or minus 3i. So our two solutions is negative 2 minus, or let's do the plus 3i first, and negative 2 minus 3i. So there's our two solutions on this one. It would not have factored because we've got this I term. We could have used the quadratic on it, but completing square worked nicely since this was a 1 and this was a 4, a nice even number. All right, here's one more rational fraction, but it's slightly different than the other because it has 3 letters. So it makes it a little bit more interesting than the one we had a while ago with just a number on the other side. I do like to go ahead and use the cross multiply method. So let's do that. Go ahead and make it where there's 2 layers on both sides. So we've got 2a times 3c plus 1 equals 1 times 5b minus c. We're going to go ahead and distribute here. So it gives us 6ac plus 2a. Now 1 times anything does not change it, so I can just bring this side down. And now you might laugh, but at this point, there's 3 letters, and I've kind of forgotten what we're solving for. So let's go back and remind ourselves. We're trying to get the C's by themselves. Well, I see a C on the left and I see a C on the right. So I'm going to bring this guy over to join his buddy. I look at this 2a. He does not have a C, so I'm going to bring him to the other side. So it gives me 6ac plus 1c is 5b minus 2a. Remember, we're trying to get the c by itself. We're trying to isolate it if you want to think about what we're trying to do. There's a c in both of these terms, so it's a common term. So if we think kind of like a GCF, we could factor it to the front of both of these, and we'd be left with 6a when we take the c here. When we divide this by c, we're left with a plus 1. This is the trickiest part, I think, right there. Remembering that if you have 2 terms, factoring out the GCF, you'll still have 2 terms. Bring the other side down, and we're almost done. All we have to do is divide by this factor on both sides. And then our c is isolated. And there's our final answer. So remember, you can use your cross multiply, or you can multiply both sides by 3c plus 1 using your common denominator method, and then go ahead and clean everything up. Remind yourself which letter you're solving for, and then do what you need to do to get those on one side and everybody else on the other. And then when you have more than one letter like this, you will always end up needing to factor it out as a GCF and then dividing. All right, so the next group of things that I want to look at that you need to do some refreshing maybe on is logarithms and exponential functions. All right, so we have a couple properties. And if you think about, in the first part of this review, we talked about exponents and their rules. So if you're multiplying two things that have a similar base, same base, you keep the base and add them up. So multiplication goes with addition. When we are dividing, bases are the same. We keep the base and we subtract. So division and subtraction go together when we're trying to do our rewrites. So when I look at this problem, I see that there's a subtraction between them. They do have the same base, so that's the one reason I can combine them. So I think of this as like they're in their own rooms. We're going to bring them together like into the big party room. Now, because it's a subtraction, we know we're going to rewrite that as a division. The positive pieces go on top, the negative goes on bottom. So if they had asked me just to rewrite it, I would have been done. But they did say, simplify this. So when I look at this, I'm going to look at the inside and see if there's anything that reduces. So I see this x will cancel out one of these. So I'm left with 27x, the one on bottom reduced. So there's my final answer. Remember, this is not a new rule. From the first week of school on, we've been talking about exponents. So when you multiply, you add. When you divide, you subtract. Logarithms use the same basic rules, the same identities, if the bases are the same. One other thing, speaking of bases, I'd like to be able to solve for this x, but there's an exponent here. So that means I would need to get the bases the same on both sides. So I need to break this 125 apart. This is where a factor tree works really, really well. I want to play with the base of 5. So does 5 go into 125? And we say, okay, that goes 25 times. Okay, again, I want to see, does 5 go into whatever number this was? And in this case, it goes twice. So I can rewrite this 125 as 1, 2, 3, 5 to the third. So now the bases are the same. So that means the exponents have to be the same. And that works out really nicely. If this would not rewrite as a factor of 5, we could then take the log of both sides and go back to solving it that way. Right? Here's a real world example of using an exponential function. So we've got our function, a equals pe to the rt, and we're using this one because this is being compounded continuously. So let's think about the a is our future value. The p is our starting value, or some people call that the principal. The r is the rate. And we need it as a decimal. So we're going to have to convert from percent to decimal to be able to plug it into the formula. And t is our time. So let's look through and see what they gave us. So did they give us the future value? No. Let's see. They gave us a 10,000 investment. So we know that is our starting amount. 6%, 8 years. So they didn't give us the future value. So that's what we're solving for. The P was our 10,000. E is a number that's found in nature and math and science. If you plug e to the first in your calculator, it will give you a very specific value. But in this case, we need to do R times T. So it gave us a 6%. We can divide that by 100 since percent is parts per 100, or we can just move the decimal place. So 0.06 times 8. So 0.06 times 8. I do like to clean up this exponent before I do put it into my calculator. That gives me 0.48. So I'm going to rewrite this one more time. All right, now I'm ready to put this into my calculator. So 10,000 using my e to the x button and putting in the 0.48 as an exponent, I get that this money will have grown in the future to 16,160.744. Okay, it's money. They want me to round to 2 decimal places. So this would be 2. So I'm looking at this 4. The 4 is not big enough to make this one round. So my final answer is this. And because it's money, I'm going to go ahead and do that. I like to make this list of numbers, and then it makes it easier to go through the problem and see what they gave me. And they are based on just writing the formula down. And anytime you have something that's being compounded continuously, you are going to use this PERT formula. All right. Logs and exponents, they just shaking hands all over the place. We looked at the exponent rules to help us rewrite the log earlier. There's another one where if we have something in log form and we're not really quite sure what to do with it, we're going to use this fun little way to transform it from a log to an exponent problem. So we start with our base. Our base is going to stay the same. And here's its exponent. So 2 to the third equals, and then we're going to set it equal to the argument part. So in generic terms, when you're rewriting this, you've got the base to the exponent equals the inside. This answer here with a log is always the exponent. All right, so let's just simplify this. 2 to the third, 2 times 2 times 2, that gives me an 8. All right, and subtract the 4. And if I were to plug it back in, I would be good to go. Remember, the inside of a log can never be 0 or a negative number. It always has to be positive. So when you're looking at your final answer, if this would make it a negative number, you would have to say no solution. All right, here's another exponential equation. They didn't tell us what it was, but it could have been something in nature that's growing continuously, like a population. I would love it if it were my money growing continuously, but they already put everything in the right place. And all we have to do now is solve for how long, solve for the t. So thinking of this like a regular algebra equation to start with, I'm going to go ahead and divide both sides by this 500. So that cancels, leaves me e to the 0.05t equals 2. And now I can either rewrite this using the exponent rule, or I can take the natural log. And the reason I chose to take the natural log is that these are the ones that are inverses of each other. If you look like squares and square roots and they are the inverses of each other, they cancel each other out, however you want to think about it. So here we go. These guys cancel. And I am still trying to solve for this t. So I'm going to divide by this number on both sides. T equals, I'm going to put this into the calculator. So the natural log of 2, close my parenthesis, divided by 0.05, and I get 13.8629. Oh, let's see, how many decimal places? 2 decimal places, so 1, 2. I have to stop here. This 2 is not big enough. Remember, it has to be 5 or more to make it round. So T would be 13.86. And I don't know if this is seconds, because this could be some kind of uranium. It could be bacterias. We don't know what it is. So I'm not going to put any units with it, because they didn't tell me up here that time was in minutes or seconds or years or 100,000 years. We don't know. All right, here's another one where if I can get the bases the same, this one comes out pretty nicely. So let's see, we need a base of 3. So let's look at this 81 and see, does 3 go into there? And if you take 81 divided by 3, you get 27. Does 3 go in again? Yes. Oh, look, all 3. So this is perfect to use where we get the bases the same on both sides. How many 3s? 1, 2, 3, 4. Bases are the same, so the exponents have to be the same. So I just solve for x, and I get x is 3. So if I were to put a 3 in here and put it in my calculator, I would get an answer of 81. All right, here's another investment problem. So they gave us a basic formula to use. Remember, this is our P, so we started with $1,000. Our rate was 0.04, and we don't know the time. Oh, yep, we do. We know T. So I'm going to go ahead and simplify that exponent times 10. So when I do that, 0.04 times 10, I get 0.4. So 1,000 e to the 0.4. They want to say, how does it grow? Okay, using this formula. So all we have to do is put this into our calculator and we will be done. So 1,000 e, which is usually a second function, 0.4, unless you're doing Desmos, then it would be built in. All right, 1491.8246. Round to 2 decimal places. That means I'm looking at this 4, not big enough to round. So 1491.82, and this is dollars. So I'm going to go ahead and put dollars with it. All right. The last thing I want to look at is graphs. We've done quite a few graphs this semester. Some of them basic function graphs, some logarithm graphs, some exponential graphs. We've talked about how to graph them easily, and keep in mind a lot of times the things we do are because they didn't have graphing calculators. So they had to find all the shortcuts. We've used this principle, a max or a min, several times. Remember, it's a quadratic, so we know it's either smiling or frowning. The negative in front tells us the basic shape is like this. So this point on top is our x and our f of x. So where is it and what is it? So this one says find the maximum or minimum value. They didn't ask us where it was, but that's step 1 is where is it? And then step 2 is to plug it into the function. Okay, so this is our good old negative b over 2a again. So let's label our a, b's, and c's. Here's our a, our b, and our c. All right. So x equals negative of b over 2 times a. A is the negative one that's in front of the x squared term. Remember, no x's go here. We're just using the coefficients. And simplifying. So x is 2. So that means what is the function, the max or min? In this case, we know it's a max. What is the max? We have to take the where question and plug it into the original function. So f of 2 equals negative of 2 squared plus 4 times 2 plus 5. We just plug it in, and then we go back and simplify. And remember, we square, good old Aunt Sally. We square this, we get a 4, and then we apply the negative. 4 times 2 is 8, plus 5 gives me 4 plus 5 is 9. So what is the max is 9. And I don't know what this is. It didn't give it to me as an application. So just f of x, or f of 2 equals 9 is our solution. Where is it? I need the x value to locate it, and then I need the x value to plug it in and find what is the actual max function. Now, if you're using Desmos, you can plug this in, and if you click on it, they will automatically put a little gray dot at the intercepts and at the max or the min. You just need to interpret what the two, they will give it to you as a coordinated pair. You just need to interpret which is which. Okay. The nice part about that quadratic formula, we use parts of it so many ways. If we want to look at the axis of symmetry, here's a square again. We know it's smiling because it's a positive coefficient. We talked about the vertex as being the actual bottom or the top. This axis of symmetry goes straight through that vertex. And if you were to think about putting this on like a coordinate axis, you can see that line would eventually intersect the x-axis. That's how we get the actual equation. So we need to know what this bottom point is. So again, let's do that. X equals negative b over 2a. Here's our a, here's our b. So negative of a negative 6, 2 times 1. So this is positive 6 over 2. So in this case, the x value is 3. Whoops, I wrote x. The x value, come on, eraser, is 3. So if you look at the first part and the last part, remember we said this line going right down the middle, like if we were to fold it, hits the x-axis. So the equation is x equals 3. And you're done for free. If you'd already been asked, like, where's the vertex, where's this, where's that on this graph, once they ask you that vertex, they're basically giving you the axis of symmetry for free. Okay, as I mentioned, intercepts is something that we like to have when we're graphing a function. It doesn't matter what kind of function. But to find the x-intercepts, that's of the form where it crosses the x-axis and the y is 0. If you're finding the y-intercepts, that means the x value is 0 and the y stays as a y. So this one is usually the easiest. So let's do it first. That means every x becomes a 0. So just substitute it in and then simplify. 0 squared is still 0. 0 times 2 is 0. 0 times negative 8 is 0. Plus 6. So that gives me a 6. So I'm going to rewrite this as a pair. So the x was 0 and the y is 6. Okay, now let's go back up here. This is where we're letting the y value be 0. So that means this y value becomes a 0. This is the one where you got to figure out your tools, see what you can do. Now, I do see that everybody is even. So I'm going to divide everybody on both sides by 2, just to make my numbers a little bit smaller. So that gives me a 1x squared minus 4x plus 6. Factors of 6 are 1 and 6 and 2 and 3. None of those add up to 4. So I can use the quadratic formula, or I can use completing the square. Doesn't really matter. We haven't done a lot of quadratic formula, so let's do that. So here's my A, here's my B, here's my C. Let's plug it into our formula. So negative of B plus or minus B squared, that was negative 4 squared, minus 4 times 1 times 6. So 2 times 1 on the bottom. All right, so we need to simplify this. Negative of a negative is a positive. Inside the radical, I've got negative 4 squared is a positive 16. Negative 4 times 1 is a negative 4 times 6 is a negative 24. And a 2 on the bottom. So at this point, sorry, I ran out of room. Let's come over here. We've got 4 plus or minus 16 minus 24. And if you're not sure, just put it in your calculator. That gives us a negative 8 all over 2. So again, this is, because it's a negative number, remember, negative 1 times the square root of 8 all over 2. So the first thing I can do is pull out the I. I need to break down the square root of 8. So 8 is 2 times 4. 4 has a really nice square root. 2 does not, but I can't factor it any further either. So 4 plus or minus I times the square root of 4 times the square root of 2 all over 2. Square root of 4 is a 2. So 4 plus or minus 2I square roots of 2 all over 2. Now, usually the directions also say simplify this. So I'm going to take both of these pieces and put them over the 2 independently. I think that makes it easier to see how you're going to reduce. So this one, 2 goes into 4 2 times. 2 goes into 2 one time. All right, so remember, these are our x values. So to put these in when the y was 0, sorry, it's a little messy here. So the 2 plus I square roots of 2 and the y was 0 would be one of them. 2 minus I square roots of 2 and the y is 0 is the second one. So this one had 2 x-intercepts and 1 y-intercept. It does help me if I write out the point. If it's an x-intercept, I'm keeping the x and I'm letting the y go to 0. If it's a y-intercept, I'm keeping the y and I'm letting the x go to 0. All right, here's a graph where they ask us to find quite a few things about the same graph. Kind of ties together a whole bunch of stuff that we've done in this class. So the domain and range, remember that's the x and the y. D comes before R, X comes before Y. That kind of helps us keep it together. So the domain talks about where does the X start and where does it stop. If you remember, it's always left to right. You're always putting the smallest one first. So look here, let's see, these are by 2's. So this is a -6. Okay. So it starts at -6. And if I travel over here, it stops at a +6. Remember, closed circles go with brackets, open circles go with parentheses. So this one had a closed circle, this one has an open circle. So I'm going to put a parenthesis. All right, similar range is bottom to top. Smallest to largest still. So I'm coming down here and I'm looking at the very bottom point, and its x value looks like a -1. Coming to the top looks like a -4. I mean, sorry, not the x value, the y value is a 2. And there is at least one closed circle at 2, so I can do a bracket. Down here, there's no open, no closed, so I'm assuming it's continuous, so I also get a bracket. So that's the first two. And then we want to know where the maxes and mins are. So in this case, let's do the max, and then we'll do the min. Now they didn't be minimal directions here, so they could be asking for the function value or they could be asking for the y value. So look at the way they wrote it. If they said find f of x, then they're looking for the y value. So I'm going to give both here. So this one is my maximum that happens at -4, and f of x, the actual maximum point, looks like it's a 2. The minimum point we said was down here. That was the lowest. When we use these, we used them to also find our domain and our range. So the smallest y value is at -1, and that occurs at x is 2. So those is our maxes and mins. All right, now increasing and decreasing. A little bit bigger here. So I'm going to draw a number line underneath this. So it starts at -6, ends at +6. And I'm going to follow like I'm on a roller coaster. I'm going to get on. And when I follow the arrows here, I am increasing until I get to -4. So I stop right there, catch my breath. And then this roller coaster continues on its journey, and it does this until it gets to 2. So stop there for a moment. Okay, and then we're going to chug back up. Maybe this is where the other landing part is. So if we were heading upwards, this would be increasing. Different color. This part is increasing. We were heading down, so this part is decreasing. And here we're heading up, so this part is increasing also. Now here, you really are only using the parentheses, because here we're not doing anything. We're stopped. We're sitting in the cart ready to go up that roller coaster. But after I leave -6, so let's do increasing, decreasing. I do both of these at the same time. So once I've done all the work, I can just come get the answers over here. So I'm increasing from -6 to -4. And then from -4 to 2, I'm decreasing. And then I start increasing again. So I'm going to use that union to stitch these together. 2, and then I stop at 6. So you see how kind of matching it up directly below with a number line, even if you're kind of drawing this on your paper or you hold your paper up right beneath it, draw the significant things where something changes, and that'll help you get your intervals. All right. Let me erase this part. We need to find where is the function greater than 0 or positive. And then we need to find where is the function less than 0 or negative. Now remember, the function itself is the y values. So we're going to be looking at this and asking ourselves, where is it positive y values and where is it negative y values? So one of the things I like to kind of do is use a highlighter. Let's see what color. Highlight, and let's do yellow. So up here, our y value is positive. Down here, our y value is negative. So when I look at this, I'm going to, come on, use that same idea of a number line again. Go back to my pen. Starts at -6, ends at +6. All right, let's look at the yellow parts. So it starts here, and it's, oh, this is too big, I'm sorry. It's only negative over here. All right. So it's yellow, starting at -6 until 0. Then from 0 to 4, it's purple. And then from 4 to 6, it's yellow. All right, so yellow we said was greater than 0. Yellow, yes, greater than 0 and greater than 0. The purple was where it was less than 0, where the y values were negative. So when I look at f of x greater than 0, well, it looks at starts at -6 and it stops being that at 0. And you see there's no equal bars here, so I'm going to only use parentheses. Okay, so there's greater than 0. And there's another part that's greater than 0. Looks like that starts at 4 and ends at 6. Now let's do the f of x less than 0. That was this little small part here from 0 to 4. And now I've got the whole graph. And you can see how the highlighting kind of functions here. It's going to be careful with your highlighter. Just this little part here was purple. All right. So they ask a lot of pieces about this. Just do it a little bit at a time and don't get overwhelmed. Use color, use number lines, anything that you can that will help you. Even if you need to make a quick sketch of this on your paper so that you can do all the highlighting and coloring and everything if you're taking this on a computer. All right. One of the other things that we talked about is, when we're looking at graphs, was, is it symmetrical? In the first part of this, we talked about transformations and a little bit more of a symmetry if you knew the actual function. Looking at a graph, we were asked, is it symmetrical to the x-axis Is it symmetrical to the y-axis or to the origin? So this means, like, could you fold it? And would it be laying right on top of itself, like when you were younger and we made the hearts? When we cut those out, they were symmetrical to a center line. So let's check for symmetry. When we check for symmetry to the x-axis, the x stays the same and the y value would change signs. When you check it with the y-axis, the y stays the same and the x changes sign. When you do it to the origin, they both change signs. So we don't have a function, so we can't like pretend we have a number or anything. So find something for yourself, some number that you can identify on this graph that makes sense to you, like maybe this one. This point is 1, -1, right? Okay. If we wrap this across the x-axis, that means 1, -1 should transform, keep the x, and change the sign on the y. So is the point 1, 1, 1, 1 on this graph? No, kind of empty space there. Right? So the next one we're going to look for is the y-axis. So we're taking this 1, 1 that we've identified that's on our original graph. With the y-axis, that means if it wraps around the y-axis, checking for symmetry, the x point would change its sign. So that would become -1, and we're keeping the y. So is -1, -1 on the graph? No. Let's check to the origin. That means the point 1, -1 that we started with, both of the signs would change. So -1, +1. So that means you wrapped it around the x-axis first and then around the y-axis, or the order doesn't matter. You could wrap it around the y-axis and then x, but the outcome is that both of the signs would change. So the -1, +1 would be right here. That's not part of our graph. So this one has no symmetry to any of the standard ones that we look for, the x-axis, the y-axis, and the origin. All right, our last two problems, I believe, are about graphing logarithms. Now, we learned some rules about how to kind of tell if they were increasing or decreasing. We learned where to put like a line of an asymptote. So let's look at this. The base is 1/2. 1/2 is less than 1. So this should be a decreasing function, which it is. They're all decreasing. Okay, that doesn't help us at all. But the asymptote comes from setting that inside greater than 0. Remember, I mentioned a while back when we were solving that inside of a log cannot be equal to 0 or a negative number. So let's go ahead and solve this. X should be greater than 1. So I'm going to come and I'm going to draw a line of symmetry where this line, an axis, where this thing, an asymptote, should not cross. And if you look at this, well, this one crosses it, this one crossed it, and this one crossed it. So here we go. Here's our final solution. So if you use what you know about basic logs, you didn't have to graph log points. You had to look for basic behavior. The base was less than 1, so it meant it was decreasing. And then to find I'm going to write the word here because I kept saying different things, sorry. Trying to find the asymptote for it, at our boundary, it got shifted from the original y-axis over 1. And so by drawing that on there or thinking about where it would be, that helps us. All right, I think the last one is also a log. Okay, again, let's use what we know about logs. The base here is 2. 2 is greater than 1, so this should be an increasing function. Are they all headed up? Yes, yes, yes. Okay, let's find our asymptote again. It's -1 greater than 0. Or you can set it equal to 0, actually. All right, so x equals 1. I'm going to draw that asymptote. And as I draw it, you should start being able to eliminate ones that are not bound by that asymptote, but that are fall within it. Do they cross it? or is it bound by it? They should be bound by it and not cross it. This one crossed, this one crossed, this one crossed. This one just used it as a nice boundary, and it also was increasing to match the base. So here we go. That will be our graph on that one. All right, that's it for the second part of the final exam review for MAC 1105 and 1105C. So I hope you found this beneficial, and good luck on your final.